Swayam Prabha. Digital India. Educated India.
Pressure is an important property of a fluid which acts normal to the surface and is compressive in nature. The unit of pressure is Pascal. Temperature is another important property of a fluid, and in fact the difference in the temperature is responsible for various convection effects that we see when boiling water. Before nucleation bubbles happen, there is a net convection roll that forms where lighter fluid from the bottom is transported towards the upper layer and it forms rolls. Density is an important property of a fluid and the unit is kg per meter cubed. Another useful way of specifying density is the specific weight, which is the combination of rho times g. This combination is quite prevalent for the case of statics, for analyzing statics. Another important parameter is the specific gravity, which is defined as the ratio of the density of the fluid under consideration to the density of a fluid at a known state, or a density of a fluid for a reference state. So the reference state can be either water or air. So specific gravity is defined as rho upon rho w or rho upon rho air. So for example, the density specific gravity of mercury is 13.6, meaning it is 13.6 times denser than water. Now we come to the equation of state. Equation of state is something which relates pressure, density and temperature for a gas. And the simplest relationship is the ideal gas relationship. It is defined as P equal to rho RT, where R is the universal gas constant for that particular gas. Now, this is a very useful equation of state for analyzing statics of gas. Similarly, we can have corrections to the equation of state, and those are called as the van der Waal corrections. And it is one of many other corrections, but van der Waal corrections accounts for the finite amount of volume occupied by molecules and also the interaction between different molecules. But what about the equation of state for liquids? There is no such equation of state for liquids, but however we can find out using empirical formulae certain relationships between pressure, density and temperature for a liquid as well. What about viscosity? Viscosity is an important property of a fluid, and it sort of accounts for the dissipation in fluids, the dissipation of energy in fluids. So consider a spoon which is dragged through a cup of water. The flow that is set up because of the motion of the spoon eventually dies down because the energy gets dissipated by viscosity. Similarly, if we have a hand fan, the motion of the hand fan gives rise to the motion of neighboring particles and it gives rise to the flow. However, if the viscosity is higher, a larger amount of fluid would be immediately displaced because of the motion of the fan, but at the same time it would make us tired because it would require a larger energy to make the motion of the fan. Let us consider what happens when a fluid element is deformed because of the action of a shear. Now the top surface has a net higher velocity as compared to the lower surface. if there was no gradient in velocity, meaning if the top and bottom velocities were to be u, there would be no deformation of the surface, but rather there would be a net translation of the fluid element. So the corollary is deformation occurs only because of gradients in velocity. Uniform velocity has no contribution towards deformation. So let us consider that the relative velocity of the top surface is delta u with respect to the lower surface. So the shear stress is found out to be linearly proportional to the rate of shear strain, that is delta theta by del t, where theta is the angle of deformation. Now if we use trigonometry, tan of delta theta in this particular case will be equal to AB upon AC. Now AB is the displacement of point A due to the gradient in the velocity. So delta U over a time delta T will cause point A to move a distance delta U times delta T. Therefore AB is equal to delta U times delta T, while AC is equal to delta Y, that is the height of the box. Therefore we can write this equal to delta U delta T upon delta Y. Now if we consider infinitesimal deformations of a fluid element, that is instantaneously what is the tendency of the fluid element to deform because of the velocity gradient, we can write tan delta theta equal to delta theta, because for small angles delta theta is approximately equal to tan delta. So delta theta is equal to delta U delta T upon delta Y, and delta theta upon delta T can thus be written as delta U by delta Y. So the rate of strain, the rate of shear strain is equal to the velocity gradient. And now using the linear relationship between shear stress and rate of shear strain, we can then write that tau is proportional to del U del Y. And because it's a unidirectional flow, we can write down del U del Y as du dy. But before that, we can introduce a constant instead of the proportionality. So we can write tau is equal to mu delta U upon delta Y, which is also equal to mu del U del Y. But in this particular case of unidirectional flow, it is mu du dy. Where is such kinds of a scenario encountered? So if we have a solid plate and if we have fluid on top of the plate and if we move a plate on top of it, it will lead to a linear velocity gradient, and there will be sort of a retarding force on the plate, and viscosity is responsible for that, and the shear stress acting on the plate will actually be equal to the viscosity times the velocity gradient. The velocity gradient in this case is u upon h. Let us now consider the temperature dependency of viscosity. Now it is a well-known fact that viscosity is dependent on the temperature. And a very common application of this dependency is that in engines. For example, motorcycle engines or car engines. So there is a crankcase, then there is the gearbox, and there is the engine head, and there are fins. Inside the crankcase, there is a lubricating oil. Now, the lubricating oil in my particular bike is 850 ml. It is also called as the engine oil. Now, the engine runs at high temperatures and splashes oil from the crankcase to the walls of the piston. And as the temperature increases, the viscosity lowers to such a point that it allows for a smooth operation. So, it is designed, it is engineered in such a way that the lowering of viscosity is appropriate for the operation of the bike. However, when the bike runs for more than 10,000 kilometers, or when you have used the bike for over 6 months, there is a lot of degradation of the oil. And the degradation of the oil is responsible for its loss in the temperature viscosity dependency. And it is at this particular point that the functioning of the oil loses its importance for the lubrication of the piston, and we have to make a change of oil. So there are certain relationships between the viscosity and temperatures, and the simplest relationship is that viscosity varies in such a way that mu upon mu naught is T upon T naught raised to n, where mu naught is the viscosity at the temperature T naught. Now, whatever we have studied so far is true when shear stress is linearly proportional to the rate of shear strain. And such kinds of fluids are called as Newtonian fluids. Most of the fluids appearing in nature are actually not behaving like Newtonian fluids. I mean, of course, under certain rate of strains, they do behave like Newtonian fluids. But in most of the cases, they actually behave in a non-linear manner. And these kinds of fluids are called as non-Newtonian fluids. That is, fluids which depart from a Newtonian behavior. So tau is proportional to del theta del t, but for the case of a Newtonian fluid, it will be a non-linear relationship between tau and del theta del t. Some of the examples of non-Newtonian fluids are ketchup, toothpaste, and in fact there are many other examples such as blood and saliva. They can be modeled as non-Newtonian fluids. Let us consider the plot of the shear stress as a function of the rate of shear strain. So on the x-axis we have the rate of shear strain or the shear strain rate del theta del t, and on the y-axis we plot the shear stress. So for Newtonian fluids it's a linear curve, while for certain kinds of fluids which have a tendency to lower the shear stress upon the increase of a shear strain rate, these fluids are called as pseudoplastic fluids. That means that given a certain strain rate, there will be a lowering of the stress for the pseudoplastic fluid as compared to a Newtonian fluid. In fact, at a given constant shear stress, the shear strain rate will be higher for a pseudoplastic fluid, or for a given strain rate, the shear stress will be higher for a Newtonian fluid as compared to a pseudoplastic fluid. And this essentially means that the viscosity of a pseudoplastic fluid reduces with an increase in the shear strain rate. Conversely, we can have the case where the shear stress at a given shear strain rate increases. And this kind of a fluid is called as a dilatant fluid. So dilatant fluid, essentially the shear stress increases with increase in shear strain rate, and these kind of fluids are also called as shear thickening fluids. That is, the effective viscosity increases with an increase in shear strain rate. Conversely, pseudoplastic fluids are also called as shear thinning fluids. That is, as the shear strain rate increases, the viscosity falls. Examples of dilatant fluids are a solution of cornstarch in water. And you can look up YouTube, you will find a lot of videos where you suddenly punch a solution of cornstarch and water and it almost behaves like a solid block. Or you can have a pool of cornstarch and water and you can run across it. But importantly, you must have a high shear strain rate to make it behave like a solid. If you gently poke the solution of cornstarch and water, it will behave like water. So for low shear strain rates, you can see from the plot as well, it behaves like a Newtonian fluid. But when the shear strain rate increases, it behaves like a shear thickening fluid. An example of pseudoplastic fluid is ketchup. As we shake vigorously the bottle of a ketchup, the ketchup begins to flow from the bottle onto our plate. Unless we shake that, unless we provide that shear strain, nothing happens. Now there are certain kinds of fluid which have an offset of shear stress before it begins to flow. That is, before it has a shear strain rate. And such kinds of fluids are called as Bingham fluids. So they have a offset of shear stress tau naught, after which they can behave like a Newtonian or a non-Newtonian fluid. And such kinds of fluids are called as Bingham plastic fluids or simply Bingham fluids. An example of a Bingham fluid is toothpaste, because until and unless you provide that offset shear stress to overcome the initial solidness of the toothpaste, you cannot cause it to flow. So that is why it doesn't flow on its own. You need to overcome that initial stress. Now, all these considerations fall under the area of research called as rheology, which is derived from the word pantharei, which means everything flows. It's a Greek phrase, and it's a term which was coined philosophically, meaning everything in life changes, nothing in life is constant, it keeps on flowing. However, it is true in the case of solids and fluids as well. Even solids flow, as we had seen in the first lecture. And all it depends is the time scale. Everything flows, but over various time scales. And it really puts into perspective that everything can be considered as a fluid and can be analyzed as fluid mechanics. So rheology is also a very important part of continuum mechanics. Now, what are the units of viscosity? The expression for viscosity, rather the shear stress for a unidirectional Newtonian fluid is tau equal to mu du dy. So it's a unidirectional flow of a Newtonian fluid. So the unit of stress is Pascal, while the unit of du dy is actually meter per second divided by meter. So meter cancels from both sides. And we simply have the viscosity units as Pascal second. Hello everyone. In this video, we are going to look at what the rank of a matrix is. But before that, We must first look at what a basis means. Basis refers to a set of elements which can span a complete set. For example, for the color space that we see in videos, R, G and B form the three primary colors with the help of which we can make any color. So any given color will be some factor multiplied by the red color plus some factor multiplied by the blue color plus some factor multiplied by the red color. And therefore a linear combination of red, blue and green can yield us the desired color. So suppose you have an image, say it's called awesome.png. When you look at the image with the help of any software such as GIMP or ImageJ or even MATLAB or OpenCV, you will see that that particular image has three channels: a red channel, a blue channel and a green channel, meaning each pixel is comprised of three different weights for red, blue and green. The weights range from 0 to 255, and for example a pixel can have a set of RGB as 128, 92 and 41. So it is 128 times the absolute color of red plus 92 times the absolute color of blue plus 41 times the absolute color of green. 255 represents that the color is completely red. So if we have 255 0 0, it means that the weightage for red is maximum while the weightage for blue and green is 0. And this is how colors are displayed on an LCD screen. Depending on the signal coming in, the red, blue or green sort of sub-pixels inside a pixel will be appropriately dimmed or brightened, therefore leading us to perceive various kinds of color through a combination of R, G and B. This table over here shows all the different RGB codes. So black is 000, which means it has 0 red, blue and green, while white is all the colors as 255. Red, as you can see, is 25500, green is 02550 and blue is 00255. And there are a host of other colors which have been showed in the chart for reference. Let us consider what the basis for vectors are. So vectors are formed typically from basis vectors. So basis vectors can be unit vectors. So a unit vector means something which has a magnitude of 1. So I, j and k are sort of unit vectors in the Cartesian coordinate system. They form a set of unit basis vectors. So any vector in a Cartesian coordinate system can be represented as ai times I plus a2 times j plus a3 times k, where a1, a2, a3 are sort of the components of the vector. The components of the vector are essentially the weights by which the unit vector has to be multiplied. But the question is whether or not the basis is unique or not. And the answer is no. I can very well choose two non-collinear vectors in the same plane to form another set. So if we consider a two-dimensional problem such as this, I can very well choose E1 and E2 to be two basis vectors. They are non-parallel. So suppose I represent in the E1, E2 coordinate system A as B1, E1 plus B2, E2. I can write down the vector which is marked by the yellow line which is along E1 as B times E1 plus 0 times E2, meaning that the vector is aligned along E1 and has no component along E2. But very well I can represent any vector as a linear combination of E1 and E2. And these bases are called as non-orthogonal bases, meaning that E1 and E2 are not 90 degrees, unlike I, J and K. So if I have any vector A, how do I find out the components of the vector A in the E1, E2 coordinate system? It's simple. I just need to take a dot product with the two basis vectors. So a dot product along E1 will tell me the component of A along E1, while the dot product along E2 will tell me the component along E2. So the elements of a basis set are necessarily linearly independent, which is to say that if I consider the RGB example, I cannot construct blue color from R or G or any linear combination of R and G. So blue stands as it says as it is, and I cannot simply represent blue as anything else. Blue is sort of a fundamental quantity which I must use to create other colors. Now, how to tell whether a set is a basis or not? Let us write down the components of the vectors I, j and k as vectors I, j and k, meaning if I look at a given column, I is comprised of 1i plus 0j plus 0k, j is comprised of 0i plus j plus 0k, while k is comprised of 0i plus 0j plus k. Now the rank of the matrix is 3. Now what do we mean by rank? Rank refers to the largest square submatrix such as this, which has a non-zero determinant. Let us check the determinant of the matrix formed. The determinant is obviously 1. Let us consider another example in which we have three basis vectors e1, e2, e3, where e1 is I plus 0j plus 0k, e2 is 0i plus j plus k, while e3 is 2i plus j plus k. Now, just by inspection, we can say that e3 is twice of e1 plus 0 times e2, meaning that E3 is a linear combination of E1 and E2, which means that E2 can be formed with the help of the two vectors E1 and E2, and hence E1, E2, E3 are not linearly independent. E3 is a linear combination of E1 and E2. It means that the rank should not be 3 because the rank is a measure of whether or not the three vectors are linearly independent or not. And this is something which you might have studied in linear algebra or which you will study in linear algebra. So clearly the determinant formed over here is 0. Now because it is 0, I must move on to the next smallest submatrix which is non-zero. So the next smallest submatrix which is square, which is non-zero, is going to be the one that I have marked. The determinant of 1001 is 1, meaning that the rank is 2. So if I consider E1, E2 and E3, it means that the choice of E1 and E2 is good enough for me to construct E3. It means that only two vectors E1 and E2 comprise the basis of the three vectors. And we have discussed already that E3 is nothing but a linear combination of E1 and E2. Let us consider another example, E1, E2, E3 as shown. Let us find out what the rank of the matrix is. Even before starting by inspection, because the k column is completely 0, the determinant formed from this will have to have a 0 determinant. The determinant of this particular matrix in which one particular sets of columns are equal, they must be 0. So then what is the rank of the matrix? That is the first question. And for a 3D basis, we know that the determinant has to be non-zero. But what is the physical meaning of the determinant being non-zero? And the hint is that the determinant is actually the operation of A cross B dot C. And A cross B dot C is nothing but the volume formed by three vectors A, B and C. And this is something which we have learned in class 11. Let us consider the matrix A as shown on the screen. The question is, what is the rank of A? Now A is a matrix of size 3 cross 4. So the smallest square submatrix that we can form will be 3 cross 3. Let us choose the first 3 columns and try to find out what the determinant will be. So determinant of this is 1 times minus 2 plus 1 times 8 minus 6, and it boils down to 0, which means that the 3 column vectors are not linearly independent. It means that there must be some vector which can be represented as a linear combination of 2 other vectors. Let us see why. It is clear through inspection that the first column is equal to the sum of the second and third columns, which is to say, if I write down the first column as A, second column as B, and third column as C, A will be equal to B plus C, which is nothing but a linear combination with weights equal to 1. Let us choose the second, third and fourth columns of the matrix A. Again, the determinant as shown on the screen is equal to 0, which means that again there must be some column vector which can be represented as a linear combination of the 2 other column vectors, because had the rank not been 0, all the 3 columns would have been linearly independent, but it is not the case. And we can see by inspection that the first column is equal to the second column minus the third column and half of this operation. So basically half times the second column plus half, minus half times the third column. So it means if I call the first column as A, second column as B, third column as C, A will be equal to half of B minus half of C, which is nothing to say that it is in fact a linear combination with weights equal to half and minus half. Let me copy the matrix A over here. Let me choose the first, third and fourth columns and see whether the determinant is non-zero or not. Once again, the determinant is found out to be 0, but I leave it as an assignment for you to find out how you can show that whether one of the columns is a linear combination of the other 2 columns. So all 3 cross 3 matrices have 0 determinants. I request you to find out the last matrix which we have not considered. There is one more 3 cross 3 matrix that we can form, but now let us look into 2 cross 2 submatrices. So let us consider the matrix as marked. So 1 1 2 0. The determinant of this is obviously equal to minus 2, which is not equal to 0, meaning that the rank of A is equal to 2, and the basis vectors are the 2 columns from which we have chosen to find the determinant. So 1 2 4 is the first column and 1 0 1 is second column. So now whatever we have discussed so far ensures us that because the rank is 2, there are 2 independent vectors which can allow us to construct the entire set of vectors that we have been given, that is the columns of A. Now can we really construct all the columns of A from only these 2 basis vectors? Let us see. Obviously the basis vectors themselves can be constructed with the basis vectors, because it is simply 1 times the basis vector plus 0 times the other basis vector. This is quite a trivial task, so I'm not going to elaborate on that anymore. What about the third column, 0 2 3? Can be constructed from the 2 column vectors, the 2 basis vectors rather. So let it be equal to A times the first basis vector 1 2 4 plus B times the other basis vector, which is 101. Let us proceed to find out each component. So the right hand side becomes A plus B, 2A and 4A plus B. Now if we equate each element of the left hand side vector and the right hand side vector, we obtain A plus B equals 0, 2A equals 2 and 4A plus B equals 3. If we solve for this linear system, we find that B is equal to minus 1, A is equal to 1. Now because we have only 2 unknowns and 3 equations, the third equation has to be consistent with the solutions that we have already found out. So if we plug in the values of a and b, we obtain 4a plus 3b is in fact equal to 3, which means that the equations are consistent. And thus, the third column vector is 1 times the first basis vector minus 1 times the second column vector. Let us do the same procedure for the fourth column. So minus 2, 2, 2 is equal to, suppose, a times the first basis vector plus b times the second basis vector. The RHS becomes the column vector a plus b, 2a and 4a plus b. Then we equate each component of the left hand side column vector and the right hand side column vector to obtain minus 2 equals a plus b, 2 equals 2a and 1 equals 4a plus b. And the solution for a and b from the first two equations are a equal to 1 and b equal to minus 3. If we plug in these values into the last equation, we do see that the left hand side and right hand side are consistent, meaning the solution is correct. And thus, because the rank was 2, we are comprehensively able to show that two vectors whose ranks are, whose determinant was non-zero, that is, which formed the basis, is indeed able to span the entire set of vectors that was given to us. The meaning of the rank of a vector is of a matrix is pretty clear. It gives us how many basis vectors there are. So if a rank is equal to 3, it means there are 3 basis vectors. If the rank is 2, it means there are 2 basis vectors. If the rank is 1, it means there is only 1 basis vector. And it means that all the other vectors in the matrix, the vectors are represented as column vectors, can be represented as a linear combination of the basis vectors that have been found out. And we have looked at it through means of a very simple example. Laws of nature do not rely on the kinds of units that we use. In fact, this means that the laws must be somehow be expressible in a dimensionless form, in a form that does not require a description through units. Moreover, this also means that the equations that we write, if they are written in dimensional form, must have a homogeneity in units. For example, the Bernoulli equation that we have learned in class 11, P plus half rho v square plus rho gz. Each of the individual terms is dimensionally homogeneous and has a unit of pressure. Let us consider some illustrative examples in which dimensionless quantities are found. Consider first the oscillation of a simple pendulum. The important parameters in the problem are the length of the string, the mass of the bob, gravity, and of course the parameter time which we want to measure. And we know that the time period of oscillation is 2 pi square root of L upon G, which we can rewrite as T upon square root of L upon G equals 2 pi. And this is a universal law for small amplitude oscillations, meaning if I take a whole bunch of uh, pendulums which have a concentrated mass, not the ones shown in the figure, but they need to have a concentrated mass at the end. They are displaced by a small amount, meaning that it's a simple harmonic oscillation in which theta equals theta. So essentially, if we take many such pendulums, we take various kinds of lengths, we can repeat the same experiment on Mars, on the moon, and you'll always find that T upon square root of L by G will be equal to a constant, and in this case it will be 2 pi. Consider the dimensions of time. It is m to the power 0, L to the power 0, T to the power 1. The dimension of length is m to the power 0, L to the power 1, T to the power 0. Dimension of gravity is m to the power 0, L to the power 1, T to the power minus 2. So what is the dimension of L upon G? It is m to the power 0, L to the power 0, T to the power 2. And the square root of this entity will have a dimension of m to the power 0, L to the power 0, T, This is the dimension of time which is on the left hand side. Therefore, T upon square root of L upon G is a dimensionless quantity, and in this particular case it is equal to a constant. Let us consider another example, that of a deflection of a cantilever beam. The important physical parameters in determining the deflection of a cantilever beam are the length of the beam, the deflection that it suffers at the free end, the Young's modulus of the material, the loading at the end, which is capital F, and the second moment of area, which is capital I. For various kinds of shapes, it has a varying stiffness. So we know that the deflection formula is given by 1 upon 48 FL cubed by EI. It's a very famous formula. We've all done it in first year mechanics. If we rearrange the left hand side and write it as delta upon L, we have delta upon L is equal to 1 upon 48 FL square upon EI. We can now rearrange the right hand side as 1 upon 48 EL F upon EL square times L to the power 4 upon I. So now delta by L is kind of the deflection aspect ratio. That is the deflection it suffers at the end in the y direction compared to the length of the rod in the x direction. And therefore it is a ratio of two lengths, and hence it is dimensionless. The term L to the power 4 upon I, okay, so the second moment of area is integral y square dA, and it has a unit of m to the power 0, L to the power 4, t to the power 0. So I has a unit of L to the power 4, whereas L to the power 4 itself has a unit of L to the power 4, and thus L to the power 4 upon I is also a dimensionless quantity. What about F upon EL square? Now F upon L square has the dimension of stress, because it is like a force per unit area. Area has a dimension of L square, whereas the Young's modulus also has a dimension of pressure or the stress, and therefore F upon EL square is also a dimensionless quantity. So thus we are able to relate one dimensionless quantity, which is delta upon L, to a combination of two other dimensionless quantities, first of which is the dimensionless loading, which is F upon EL square, and the second of which is the dimensionless second moment of area. As long as all the units are consistent, this law gives us a universality in which we can choose a large number of cantilevers of varying lengths, and given that all the deflections lie in the elastic limit, all the deflections for all the various Young's modulus, all various shapes are expected to follow this kind of universal behavior. Both the examples that we have seen, it is fairly clear that we can sort of eyeball the problem and get what kind of terms will be involved in forming of the dimensionless solution. However, in case where there are a lot of terms, we need to find out a general method to do it. We cannot always rely on eyeballing it. General method was proposed by Buckingham, and the name of the theorem is famously called as the Buckingham pi theorem. In this theorem we have n parameters, and if the rank of the dimensionless matrix is R, we'll look at what these things are. Then the problem has n minus R number of dimensionless groups. So if we consider that we have 7 parameters v1, v2, v3, v4, ijk as 7 vectors in this particular example, then I, j and k serve as 3 independent vectors, meaning the rank of the matrix would necessarily be 3, and we have already covered this in the mathematics video. And it means that I, j and k can be used to construct forms which can represent v1, v2, v3 and v4 as a linear combination of I, J and K. And thus V1, V2, V3, V4 are sort of combinations of I, J and K. Similarly, if we have terms such as P1, P2, P3, P4 and the rank is 2, meaning we have two independent vectors, then P1, P2, P3 and P4 can be formed out of a linear combination of P5 and P6. So the various dimensionless terms are called as the pi terms, and we can write down pi1 as P1 times P5 raised to A, P6 raised to B, and eventually it is our task to find out what the values of A and B will be, which would satisfy the fact that pi1 has no dimension. Similarly, we can write down pi2 as P2 times P5 raised to A and P6 raised to B. And then once again, the task would be to find out the values of A and B so that pi2 has no dimension as well, and so on. On our earlier discussion of the fact that if we have dimensionless parameters appearing in the equation, we should be able to find some kind of relationship between all the dimensionless terms. So in the end, we can sort of construct a relationship between the various pi terms, or effectively we can also express any one pi term in terms of the other pi terms. Typically, the pi term that we express in terms of the other pi terms is the kind of parameter that we really want to find out. In the earlier illustrations, it was either the time of oscillation or the deflection of the cantilever beam. Now remember that this is a very hypothetical example for the case where the rank is 2. Now we consider the 7 steps to non-dimensionalization. First step is to identify the important parameters and variables in the problem. Let us consider as an example the flow of a viscous fluid through a pipe. The diameter of the pipe is d, the average velocity is capital U, the length of the pipe is delta x, the roughness of the surface of the pipe is denoted by epsilon, and we want to know what is the relationship between the pressure drop and all the various terms. The other two important fluid parameters are fluid density and the fluid viscosity. So it is very important to first assess all the various physical parameters arising in the problem. The second step involves writing down a dimensionless matrix. So we'll list out all the various parameters and variables that we have obtained in the first step in a column-wise manner. In a single row, we write them out. In the columns corresponding to these variables, we write down the exponents of m, l and t. So for example, the exponent of m, l and t for delta x, which is nothing but the length of the pipe, is 0 because it is m to the power 0, 1 because it is l to the power 1, and again 0 because it is t to the power 0. In this way, write down all the exponents of m, l and t. Third step happens to be finding out the rank of the dimensionless matrix that we have found out. So why would we want to know the rank of this matrix? Because from the entire set of parameters, we would like to know which parameters are linearly independent of each other and which parameters form the basis with the help of which we can write down an expression for all the other parameters. Essentially, we want to find out the basis, and hence we need to find out the rank. If the rank is equal to 3, it means there are 3 independent basis parameters that exist, and these parameters will allow us to construct all the other terms. Essentially, we can then represent all the other terms as a dimensionless quantity. We'll see it as we progress. So, what is the rank of this particular matrix? Let us choose the three columns as delta x, d, and viscosity. So, immediately it is clear that the determinant is equal to 0. But this is not the only 3 cross 3 submatrix that we can find, because after all, finding the rank is finding the non-zero, the largest non-zero submatrix. And this is covered in the video already. So let us now choose the velocity, the density, and the viscosity. The determinant of this particular 3 cross 3 submatrix tends to be -3 and it is non-zero. As a result of which, we can conclude rank of the matrix is equal to 3. And from Buckingham pi theorem, we know that if there are n number of terms and variables and the rank is equal to 3, so 7 minus 3, which is equal to 4, will be the number of pi terms that we will have. So 4 dimensionless groups. For proceeding, let us choose the velocity, diameter, and the density to be the basis vectors. But before ascertaining whether they are really the basis vectors, let us quickly check whether the submatrix formed using these three parameters are indeed non-zero. And it does come out to be equal to -1, which is not equal to 0. So we can choose u, d, and rho to be a basis for all the other terms. Now comes the important part, finding out the pi terms. So the first pi term, let us find out the non-dimensional form of the pressure in terms of the basis vectors u, d, and rho. So we have pi 1 is equal to delta p times u raised to a times the diameter raised to b times the density raised to c. Let us write down the dimensions of each term. So pressure is m to the power 1, L to the power minus 1, t to the power minus 2. The term involving the velocity is m to the power 0, L to the power 1, t to the power minus 1 whole raised to a. The term involving the diameter is m to the power 0, L to the power 1, t to the power 0 whole raised to b. The term involving density is m to the power 1, L to the power minus 3, t to the power 0 whole to the power minus 3. Now let us write down the exponents of m. The exponent of m is 1 plus c. The exponent for length is -1 plus a plus b minus 3c, while that of time is -2 minus a. Now we know that pi 1 by definition is going to be a dimensionless quantity, as a result of which each exponent of m, l, and t must be equal to 0, so that in the end we obtain m to the power 0, l to the power 0, t to the power 0. So let us set 1 plus c equals 0, -1 plus a plus b minus 3c equals 0, -2 minus a equals 0, yielding a equal to -2, c equal to -1, and b equal to 0. As a result of which, the first pi term is equal to delta p u to the power -2, d to the power 0, rho to the power -1. And thus we have the first pi term as delta p upon rho u square. And we know from Bernoulli equation that yes, pressure does have the same units as rho u square, as a result of which we can express the dimensionless form of pressure as delta p by rho u square. Let us now proceed to find out the other pi terms. So apart from the basis vectors The next term that we consider is the length of the tube, which is delta x. So we have delta x multiplied by u raised to a, d raised to b, and rho raised to c. And it is very easy to see that delta x has the unit of length, while the diameter has also the units of length, as a result of which the non-dimensionalization of the length of the tube must necessarily be delta x upon d, which means a will be equal to c will be equal to 0 and b will be equal to minus 1, yielding the second pi term to be delta x upon d. Similarly, the third pi term involves the surface roughness of the pipe, which is epsilon, and so the pi 3 will be equal to u raised to a, d raised to b, rho raised to c multiplied by epsilon by the same arguments as we've made for the length of the tube. The third pi term will also be equal to epsilon upon d. As for the fourth pi term, which is representing viscosity in terms of the basis vector. So pi 4 is equal to mu u to the power a, d to the power b, rho to the power c. Putting in the dimensions of mu, which is m to the power 1, l to the power minus 1, t to the power minus 1, and plugging in the values of the dimensions of velocity, density, and rho, exponentiating them to a, b, and c respectively, we can then collect all the various exponents of m, l, and t and equate each power to 0. We obtain a equal to minus 1, c equal to minus 1, and b equal to minus 3 by solving the system of linear equations formed from setting each coefficient, or rather each exponent of m, l, and t to be 0, because by construction, again I am repeating, pi 4 has to be dimensionless. Therefore, the fourth pi term will be equal to mu upon u d rho, which an advanced or an observant user will recognize as the inverse of Reynolds number. Hence, we can write down a relationship between pi 1, pi 2, pi 3, and pi 4. And more explicitly, we can write down the relationship between pi 1 as some function of pi 2, pi 3, and pi 4. And the diagram which represents this kind of grouping of parameters is called as the Moody's diagram. And while this is the sixth step, the seventh step is to actually perform some experiments and find out the exact nature of the relationship between the various pi terms. So, for example, delta p, dimensionless delta p, depends linearly on the length of the pipe, meaning pi 1 and pi 2 have to be in the numerator. It cannot be such that pi 1 is proportional to 1 upon pi 2. That will not work because the delta p cannot go down as the length of the pipe increases. So these are certain things which are driven usually by a fundamental understanding of the actual process or by means of some experiments. In the Moody's diagram on the y-axis, we have the friction factor, which is nothing but delta p upon, we have delta p upon rho v square multiplied by d upon L. So essentially, this is sort of pi 1 divided by pi 2. On the x-axis, we have the Reynolds number, which is essentially 1 upon pi 4 for us, and the various curves have been plotted for relative pipe roughness, which is epsilon upon d, the ratio of the roughness of the pipe to the diameter of the pipe. And it's a very neat way of representing data without going too much into the specifics of a certain experiment.